Spar Torpedoes. In the 1860s, the word torpedo did not necessarily mean a metal cylinder racing through the water. It could mean an explosive charge sitting underwater, attached to a boat, or fixed to the end of a long pole. That last version was the spar torpedo. A small craft carried a long wooden or metal spar projecting from its bow, with an explosive charge mounted at the far end. The crew had to drive directly toward the target, press the charge against or beneath the enemy hull, and detonate it. There was no seeker, no engine inside the weapon, and very little distance between attacker and explosion. During the American Civil War, both Union and Confederate forces experimented with these weapons. The Confederate semi-submersible David damaged USS New Ironsides with a spar torpedo in 1863. The following year, the submarine H.L. Hunley sank USS Housatonic with a similar concept, becoming the first combat submarine to sink an enemy warship, though Hunley itself was lost as well. Union Lieutenant William B. Cushing used a spar torpedo from a steam launch to sink the Confederate ironclad Albemarle. These were torpedoes according to the language of the time. The word had originally been applied to underwater explosive devices more generally. Static charges eventually became known as mines, while torpedo gradually narrowed toward the self-propelled weapon we recognize today. That distinction matters because there is no single clean list of torpedo types. A modern weapon might simultaneously be heavyweight, submarine-launched, wire-guided, active and passive acoustic homing, and thermally powered. Those descriptions refer to different parts of the same weapon. So the easiest way to understand the family is to follow the problems engineers were trying to solve. The first problem was obvious. How do you hit a ship without carrying the bomb all the way there yourself? Straight-running torpedoes. Robert Whitehead supplied the answer in 1866. His automobile torpedo, as self-propelled torpedoes were initially called, had its own compressed air engine. Once launched, it moved through the water independently. An early Whitehead design managed only about 6.5 knots for roughly 200 yards. Hardly impressive beside a modern torpedo, but the principle changed naval warfare. The attacker no longer needed to ram an explosive charge against the enemy. The explosive could swim there by itself. Early self-propelled torpedoes were essentially straight runners. The launching platform calculated where the target would be, aimed the weapon accordingly, and sent it away. The torpedo did not look for anything. It simply tried to maintain the course and depth it had been given. That turned out to be harder than it sounds. A torpedo is moving through dense water, not air. Small errors can make it roll, dive, climb, or curve away from its intended course. Whitehead used depth control mechanisms and counter-rotating propellers to improve stability. Later designs added gyroscopic steering. The United States also experimented with John Howell's torpedo. Instead of compressed air, the Howell used a heavy flywheel that was spun rapidly before launch. That flywheel both stored energy for propulsion and produced a gyroscopic stabilizing effect. The U.S. Navy eventually ordered about 50 of them. By the early 20th century, a straight-running torpedo could travel much farther and faster than Whitehead's first machine, but its basic logic remained simple. Launch it on the correct line and let physics do the rest. Straight running did not mean the weapon had to physically crash into the side of a ship to explode. Torpedoes also evolved different fusing systems. A contact exploder detonated when the torpedo struck its target. An influence exploder attempted to detect some property of the ship, such as its magnetic field, allowing the warhead to detonate nearby or beneath the hull. That sounded particularly attractive against heavily protected warships because an underwater explosion beneath the keel could attack the ship's structure rather than simply punching into its side. But sophisticated did not always mean reliable. Early in World War II, the American Mark XIV became notorious for a combination of depth control and exploder problems. Its magnetic influence mechanism could detonate prematurely, while the contact mechanism could fail even after a direct hit. The problems were serious enough that U.S. submariners gradually forced a reassessment through combat experience and testing. A torpedo could have an excellent engine, a large warhead, and an apparently clever detonator, yet still be useless if one small mechanism failed at the last second. The next generation tried to solve another weakness. What if the torpedo missed the target's original position? Gyro and pattern-running torpedoes. Adding a gyroscope meant the torpedo no longer had to leave its tube already pointing exactly along its final path. A preset gyro could make the weapon turn after launch and then settle onto the required heading. That gave ships and submarines much more freedom in how they launched their weapons. But it was still following instructions written before launch. During World War II, German engineers pushed that idea further with pattern-running torpedoes. The FAT system, nicknamed Curly by the Allies, could begin with a conventional straight run and then start moving back and forth through an area. It was particularly useful against convoys, where missing one ship did not necessarily mean there was nothing else nearby. Instead of continuing uselessly into empty ocean, the torpedo could sweep across the convoy's path more than once. A more refined system called LUT allowed greater flexibility in how that search pattern was oriented. Neither system truly hunted a target. The torpedo did not hear a propeller and decide to chase it. It was executing a mechanical program. Think of it as the difference between a robot following a pre-written route and one using sensors to follow someone moving through a room. Allied intelligence regarded pattern-running weapons as a significant development because they increased the probability of a hit without requiring the torpedo to understand what it was looking for. Then, engineers gave torpedoes ears. Passive acoustic homing torpedoes. A passive acoustic torpedo listens. It sends out no sonar pulse of its own. Instead, hydrophones inside the weapon detect noise already present in the water and use that sound to guide the torpedo. Propellers, machinery, and other moving components can produce acoustic signatures. If the weapon can distinguish the desired sound from everything else around it, it can continually correct its course, instead of depending entirely on a firing solution calculated before launch. This was one of the biggest changes in torpedo history. During World War II, the United States introduced the Mark 24, nicknamed Fido. Officially, it was disguised as a mine because its real function was secret. In reality, it was an air-dropped passive acoustic homing torpedo designed to attack submarines. It entered combat in 1943. Germany fielded its own acoustic weapons. The T-5 Zaunkönig, often described by German crews as a destroyer killer, listened for propeller noise after an initial straight run. For an escort vessel chasing a U-boat, this created an ugly problem. The destroyer's own propellers could help the torpedo find it. The response was equally revealing. Allied ships began towing noise-making decoys. If the torpedo wanted sound, the defenders would give it a louder, more attractive sound somewhere else. That started a contest that still defines undersea warfare: seeker versus countermeasure, followed by improved seeker, followed by improved countermeasure. Passive homing has one major attraction. The torpedo does not need to announce itself by transmitting sonar. But listening alone has limitations. The ocean is noisy, reflections are complicated, and a quiet target may not give a passive seeker much to work with. So another type does something much less subtle. It starts pinging. Active acoustic homing torpedoes. An active acoustic torpedo carries sonar. It transmits sound into the water and listens for echoes. Instead of asking, "What is making noise?" it can ask something closer to, "What solid object is reflecting my signal?" That means the target does not have to cooperate by being loud. Active sonar can help a torpedo search for a quiet submarine, particularly when the approximate target area is already known. U.S. Navy environmental documentation describes active torpedoes as transmitting acoustic signals and using the returned echoes for guidance. There is a trade-off. A transmitting seeker is less discreet than a purely passive one. An active pulse is useful information for the weapon, but sound propagating through the water can also reveal that something is searching. Modern torpedoes therefore do not have to live permanently on one side of the active versus passive divide. Weapons such as the U.S. Mark 48 family are described publicly as having both active and passive homing capability. That allows different sensing behavior as an engagement develops. This hybrid approach is often called dual mode or active-passive homing. And that is an important reminder about torpedo categories. A passive torpedo, active torpedo, and wire-guided torpedo are not necessarily three completely different physical weapons. One torpedo can do all three things at different stages. Which brings us to the thin line that sometimes runs behind a modern heavyweight weapon: wire-guided torpedoes. A wire-guided torpedo remains connected to its launching submarine by a very fine guidance wire after it enters the water. That sounds almost absurd when you picture a powerful underwater weapon traveling away from a submarine with a wire unreeling behind it, but the connection solves a major problem. A torpedo has limited sensors. The submarine that launched it has a much larger combat system and may continue receiving information about the tactical picture. Wire guidance allows updated information to reach the weapon instead of forcing it to rely forever on what was known at the instant of launch. Eventually, the torpedo can rely more heavily on its own seeker. The principle has existed for far longer than modern digital torpedoes. Wire-controlled weapons were being experimented with in the 19th century. The idea became much more important once submarines had the sensors and computing power to take advantage of it. Modern public examples include Britain's Spearfish heavyweight torpedo, which the Royal Navy describes as capable of guidance by wire or by its own sonar. The U.S. Mark 48 family has also used wire guidance. The wire is not there because the torpedo is incapable of homing. It gives the launching platform another way to influence the weapon before autonomous guidance takes over. A very different seeker ignores much of this acoustic contest. It does not primarily hunt the ship. It hunts the trail the ship leaves behind. Wake-homing torpedoes: a large vessel disturbs an enormous volume of water as it moves. Its propellers churn the sea. Bubbles appear. Pressure, density, and turbulence change. Behind the ship is a wake that can persist after the hull itself has moved on. A wake-homing torpedo tries to detect that trail. One publicly described approach uses an upward-looking sensor to recognize the disturbed water. Once the weapon finds the wake, it can work its way along it toward the vessel that created it. This produces an awkward defensive problem. An acoustic decoy can imitate machinery noise. It cannot easily erase the physical trail a large ship has already carved through the water. Researchers at Penn State's Applied Research Laboratory have described wake-homing torpedoes as crossing the edges of a ship's wake repeatedly while following it toward the source. U.S. naval analysts have treated such weapons as a particularly difficult threat for conventional acoustic countermeasures. Wake-homing is therefore mainly associated with attacks on surface ships rather than submarines deep below the surface. Now we can divide torpedoes another way. Not by how they think, but by how large they are and what job they are expected to perform. Heavyweight torpedoes. Heavyweight torpedoes are the large weapons most strongly associated with submarines. The U.S. Navy's Mark 48 gives a good sense of the class. It has a diameter of 21 inches and weighs roughly 3,744 pounds. It is designed for both anti-submarine and anti-surface warfare. That versatility matters. A submarine may encounter another submarine, a surface combatant, or a large vessel with very different acoustic and movement characteristics. A heavyweight weapon has the volume for a substantial warhead, propulsion system, sensors, control electronics, and the endurance expected of a submarine's primary torpedo. Britain's Spearfish occupies the same general category, weighing close to 2 tons. Heavyweight does not describe its seeker. It does not tell you whether the weapon is active, passive, wire-guided, or something else. It tells you about the broad size class and, by extension, the platforms and missions for which the weapon has been designed. Historically, some navies went even larger. Japan's Type 93 of World War II had a diameter of 24 inches. Its propulsion system used compressed oxygen rather than ordinary compressed air, contributing to remarkable performance for the period and a relatively small visible bubble wake. U.S. forces underestimated its capabilities early in the Pacific War, sometimes with disastrous results. The Type 93 is sometimes treated as if it were a completely separate species of weapon. It was not. It was an extreme answer to the same heavyweight problem: put enough speed, range, and explosive power into a torpedo to make major surface warships vulnerable at distances they might consider safe. At the other end is a torpedo designed around a very different constraint. It has to be small enough for an aircraft to carry. Lightweight torpedoes. A lightweight torpedo is usually an anti-submarine weapon. The US Mark 54 weighs about 607 pounds and has a diameter of 12.75 inches, dramatically smaller than a Mark 48. It can be launched from surface ships and aircraft. That size difference reflects the mission. An aircraft carrying a torpedo does not need the weapon to swim from the aircraft all the way to a submarine hundreds of miles away. The aircraft does the long-distance transportation. It uses radar, sonobuoys, and other sensors to help locate a submarine, travels to the area at aircraft speed, then releases the torpedo into the water. The torpedo only has to perform the underwater portion of the hunt. Surface ships can launch lightweight torpedoes as well, making the same weapon useful across helicopters, maritime patrol aircraft, and warships. Earlier American examples included the Mark 44 and Mark 46. Over time, lightweight weapons gained increasingly capable acoustic seekers and digital processing, while remaining small enough for airborne carriage. Lightweight and heavyweight torpedoes can therefore possess similar kinds of guidance technology while having very different bodies and launch platforms. A Mark 54 is not less intelligent because it is lighter. It simply has a different job, and sometimes the strangest part of that job happens before the torpedo even touches the water. Air-dropped torpedoes. The first American air-dropped torpedo test took place in 1920. The idea created its own engineering headache. A submarine-launched torpedo begins already surrounded by water. An aircraft torpedo has to survive falling through the air, striking the sea, stabilizing itself, reaching its operating depth, and then behaving like a normal torpedo. Early aircraft torpedoes were especially sensitive to release conditions. Too violent an entry could damage the weapon or send it into an unstable run. Yet aircraft gave torpedoes something ships and submarines could not match: rapid delivery from above. During World War II, specialized torpedo bombers made low-level attacks against surface ships. Later, the air-launched torpedo shifted increasingly toward anti-submarine warfare. Fido was an early example of that transformation. Modern maritime patrol aircraft and helicopters can carry lightweight homing torpedoes such as the Mark 54. An airdrop torpedo is therefore categorized by delivery, not necessarily by guidance. The moment it reaches the water, it may become an active acoustic torpedo, passive acoustic torpedo, or a weapon that combines both. There is also a way to throw a torpedo much farther from a surface ship without putting an aircraft overhead. Attach it to a rocket. Rocket-delivered torpedoes. A rocket-delivered torpedo creates a weapon inside another weapon. The U.S. Vertical Launch Anti-Submarine Rocket, or VLA, illustrates the idea. A surface ship launches the rocket from a vertical missile cell. The rocket carries a lightweight torpedo through the air toward the area of a suspected submarine. Near that area, the torpedo separates, enters the water, and begins operating as an underwater weapon. The rocket is not the torpedo. It is the delivery vehicle. The U.S. Navy's VLA has been used to deliver Mark 46 and Mark 54 lightweight torpedoes. This solves a simple problem of geometry. A ship may detect a submarine outside the convenient reach of a directly launched lightweight torpedo. Sending the torpedo through the air covers the initial distance much faster than making the torpedo swim the whole way. The concept goes back to Cold War anti-submarine systems and continues because water is an expensive medium in which to travel quickly. That leads to another way torpedoes differ. What actually turns the propeller? Electric torpedoes. Electric torpedoes use batteries and electric motors for propulsion. The concept became especially important during World War II. Traditional wet heater and other thermal torpedoes could leave visible bubble wakes from their exhaust. An electric torpedo could be much harder to spot from the surface because it did not need the same exhaust process. German electric torpedo technology attracted intense Allied attention. After U-570 was captured in 1941, the United States gained access to German designs, and the American Mark 18 entered service soon afterward. The U.S. Navy described electric propulsion's major advantages at the time as a reduced visible wake and simpler manufacture. Electric propulsion also suited acoustic homing weapons because machinery noise matters when the weapon itself is listening. But batteries contain only so much stored energy, and historically electric torpedoes often traded speed or endurance for quietness and simplicity. Battery technology has improved enormously since then, so the old stereotype of the slow electric torpedo is not a universal law. Still, the underlying bargain remains recognizable. Electric systems avoid combustion machinery and exhaust, while thermal systems can offer very high energy density. And thermal propulsion is a much larger family than the early compressed air torpedo suggests. Thermal torpedoes. Whitehead's first practical torpedoes used compressed air to drive their engines. Engineers soon realized that compressed air alone left a great deal of potential energy unused. Heating the air before it entered the engine increased performance. Later systems burned fuel with an oxidizer, producing hot gas or steam to drive turbines or piston engines. This produced several generations of what are broadly called thermal torpedoes. The American Mark 14 used a steam turbine system based on compressed air and alcohol combustion. Japan's Type 93 took another route by using oxygen-rich propulsion. German engineers experimented with hydrogen peroxide systems near the end of World War II. Modern thermal propulsion can be quite different again. The US Mark 48 family uses Auto Fuel 2, a liquid monopropellant. Monopropellant means the fuel does not need to mix with atmospheric oxygen in the way gasoline burns in a car engine. The necessary chemistry is carried inside the weapon. A Mark 48 propulsion system publicly described by Naval Sea Systems Command uses a hot gas piston engine driving a pump jet. The details have changed dramatically since Whitehead, but the objective has not. Fit as much useful underwater movement as possible into a long cylinder that also needs room for sensors, control systems, and a warhead. Most torpedoes still move by pushing water backward with propellers or pump jets. One famous type decided that water itself was the problem. Supercavitating torpedoes. Water is roughly 800 times denser than air. That density makes underwater weapons brutally resistant to extreme speed. Push an ordinary torpedo faster, and drag rises sharply. Supercavitation attacks that problem by trying to keep most of the weapon from touching the water at all. A supercavitating torpedo creates a large gas cavity around its body. Instead of the entire hull rubbing against liquid water, much of it travels inside that bubble. The best-known operational example is the Soviet VA-111 Shkval. Public Western analysis describes Shkval as a rocket-powered underwater weapon capable of speeds on the order of 200 knots, far beyond conventional torpedo speeds. It uses a gas cavity around the vehicle to reduce hydrodynamic drag. That speed sounds like the answer to every torpedo problem. It is not. The same bubble that reduces drag complicates sensing and maneuvering. A conventional homing torpedo can spend time listening, searching, and changing course. A supercavitating weapon is built around a much more violent hydrodynamic environment, so supercavitation is not simply normal torpedo, but better. It is a specialized trade. You gain extraordinary speed by accepting different limitations in guidance, maneuvering, and design. There is another torpedo type whose defining feature has nothing to do with speed. The difference is in the warhead. Nuclear torpedoes. During the Cold War, both sides confronted an uncomfortable problem. Nuclear submarines were becoming faster, able to remain submerged for long periods, and increasingly difficult to destroy with older anti-submarine weapons. One American response was the Mark 45 ASTOR, short for anti-submarine torpedo. ASTOR entered service around 1960 and carried a nuclear warhead. Unlike later sophisticated homing torpedoes, it relied on wire guidance rather than an autonomous terminal seeker. The nuclear explosive meant the weapon did not need the precision expected from a conventional torpedo. That also produced a grim joke among submariners. A weapon with a large underwater nuclear detonation could threaten more than the target. ASTOR remained in service until the 1970s and was replaced by the conventionally armed Mark 48 as homing technology improved. The Soviet Union also fielded nuclear-capable torpedoes during the Cold War. This category should not be confused with nuclear-powered torpedoes. Nuclear torpedo normally refers to the warhead, not to a nuclear reactor driving the weapon through the water. The distinction matters because almost every normal torpedo propulsion system is limited by the energy physically stored inside it. A nuclear warhead changes the explosive effect. It does not automatically change how the torpedo swims. One historical type changed something far more fundamental. Instead of building a better guidance computer, its designers put a human being inside. Human torpedoes. In 1944, Japan began developing the Kaiten. The name is commonly translated as something like turning the heavens, but its function was much less poetic. The operational Type 1 Kaiten was built around technology from the Type 93 torpedo. Engineers enlarged the weapon, added a pilot compartment with controls and a small periscope, and gave the pilot the task normally handled by a guidance system. Early ideas included a possible escape arrangement. Operational production models effectively turned the Kaiten into a suicide weapon. The pilot was locked inside. Kaiten were carried by submarines to an attack area and then released. In theory, a human pilot could compensate for errors that defeated a straight-running torpedo. He could observe, steer, and make corrections. In practice, the system was extremely dangerous even before combat. Training accidents killed pilots. Mechanical problems were common. Combat effectiveness remained limited compared with the cost in lives and resources. Kaiten did sink the American fleet oiler USS Mississauga in November 1944 and were responsible for other losses, but they never delivered the strategic effect their designers wanted. Italy, Britain, and Germany also developed manned underwater attack craft during World War II, though many of those were closer to miniature submersibles carrying detachable explosives than true impact torpedoes. That distinction is why human torpedo can be a confusing label. Some were vehicles that carried swimmers toward a target and let them return. Kaiten turned the entire vehicle into the weapon. The final category reverses almost everything we have covered so far. For more than a century, the torpedo's target was a ship or submarine. Then engineers began building torpedoes whose target was another torpedo. Anti-Torpedo Torpedoes. The normal defense against a homing torpedo has traditionally been some mixture of maneuver, noise-making decoys, jammers, and other countermeasures. Those are soft-kill defenses. They try to make the weapon miss. An anti-torpedo torpedo attempts a hard kill. It physically intercepts the incoming weapon. The concept sounds like underwater missile defense. A sensor system detects a hostile torpedo, tracks it, launches a much smaller interceptor, and the interceptor uses its own guidance to reach the threat. The U.S. Navy tested a system called the Countermeasure Anti-Torpedo, or CAT, aboard aircraft carriers. It was paired with a torpedo warning system as part of a larger surface ship torpedo defense effort. Tests demonstrated some ability to intercept incoming torpedoes, but reliability and overall effectiveness remained problematic. In September 2018, the Navy suspended development of that surface ship system and planned to remove the equipment from its carriers. The program's difficulties show why this is such a hard problem. A torpedo is already a relatively small object, moving through a noisy, cluttered three-dimensional environment. Now the interceptor has to detect that weapon, distinguish it from everything around it, predict where it is going, and collide with or destroy it before the original torpedo reaches the ship. So after more than a century and a half of torpedo development, the family has come almost full circle. The Spar torpedo needed a person to carry an explosive directly to a ship. The Whitehead torpedo carried itself. Pattern runners followed mechanical instructions. Acoustic torpedoes learned to listen. Active seekers learned to search. Wire-guided weapons remained connected to the submarine that launched them. Wake homers followed the disturbance a ship left behind. Heavyweights became a submarine's major multi-purpose weapon. Lightweights gave aircraft and surface ships a compact submarine hunter. Rockets carried torpedoes through the air. Electric and thermal systems competed over how best to move them. Supercavitation traded conventional behavior for extreme speed. Nuclear torpedoes traded precision for enormous destructive radius. Human torpedoes replaced the guidance system with a pilot, and the anti-torpedo torpedo gave the weapon a new target, itself. That is why there has never really been one final type of torpedo. Every generation solves one problem and creates the next one underwater.